heard the beginning of Bach's Toccata in D minor, a really famous piece which is really useful to evaluate new instruments. In Bach's days it was used to test if an organ had enough wind to support all those stacking chords. Today we will evaluate my microcontroller project. My microcontroller does not need any wind, but it needs to be programmed efficiently enough that we don't run out of CPU by producing all those polyphony. This short excerpt also demonstrated a few other things. You might have noticed that I could use my left pedal to switch the pre-programmed registration. I could use the sostenuto pedal to hold the pedal notes, which went to the pedal instrument denoted by P in the task list, as opposed to the upper notes, which went to the Hauptwerk instrument denoted by HW in the task list. What probably went unnoticed is that those pedal notes went through an octave 8-fuse coupler, which means also, although I already played an octave, those two notes were again doubled an octave below before they went to the real instrument. So in the pedal were really 4 notes playing. Let's test it to the maximum. I'll play 4 notes as before in the pedal with the help of the octaver and the full 16 notes in the Hauptwerk. So, how does it work? When a key is pressed, the MIDI out signal of my keyboard is received by my self-built MIDI in socket. It is quite close to official specifications. It also uses a PC900V as opto isolator, but the microcontroller, the RP2350, only provides 3.3 volt. I only lowered the resistor slightly to 270 ohms, and to protect against any misconfigurations, I used an additional 100 ohms just in front of the GPIO pin, just to be safe. This pin is configured as UART receiver pin and read by my MIDI parser. This information then is passed through a network of couplers which modify it and route it to the intended instrument. This network, as well as the instruments, can be configured by a text file. Instruments may have their own unique way to generate sound from those informations and store those informations about the sound in a first in, first out buffer of the mixer. The mixer then takes all those information, mixes them together in one single output signal, which then the YAHAL library takes from a circular buffer and puts them out on a GPIO pin via pulse width modulation. This output pin is then connected to a 3.5mm jack, in which we simply can plug in our speakers. Let's be honest for a moment. It's near impossible to beat the feeling of playing a real organ. But this microcontroller project has a huge advantage over normal electronic pianos and especially over real organs. It's very tedious to tune those. And it's impossible to do this dynamically, which we need for pure tuning based on the harmonic series. I've implemented a coupler that acts as a proof of concept that tuning dynamically is possible. It only uses the last pressed key as context. But this is sufficient to show that the pure circle of fifth really is a spiral. We'll start in tune with my regular piano and end out of tune once we've returned to C. So with this microcontroller project, I've successfully established a basis for further experimentation on tuning and microtonality.